Hello everyone, welcome back for part 2 for section 2 for torque. So we're just going to jump right in. So we have here immobile. This should look familiar. This was from one of the handouts that I gave you in class. And the goal here is to figure out what the masses of these other three objects are. So let's jump right in. So we know that torque is equal to force times distance, where it's the force exerted by the object times the distance to the pivot point. So in this case, the pivot points are going to be the points where the string is hanging from, these 3 points here. So it's worth noting that because these are masses hanging from an object, the force that they exert is equal to the force that Earth exerts on them. So the force that they exert on the bar is going to be their mass times g, and then times distance. And we'll talk about a shortcut of this later. So anyway, the next thing we need to remember is that in order for an object to be in equilibrium, like this mobile is, the net torque has to be 0. That means that the torque on one side is equal to the torque on the other. Or the other way of talking about it is that because we're saying that the net torque is equal to 0, that any torque that is in one direction will be positive, and any torque that is in another direction will be negative, that we determined ahead of time. This should sound all very familiar. And so when you add those torques together, it is equal to 0. So for the sake of this handout, let's say that counterclockwise is positive. Okay, so any torque or any force that causes a counterclockwise rotation or counterclockwise torque will be positive. So let's start. So here we have our 2 torques. We have one caused by a 0.3 kilogram mass. We have another one caused by a mass of unknown amount. And so if these are in equilibrium, then we have the net torque is equal to 0. So we have the torque from the 0.3 kilogram, which is going to be positive because it causes a rotation this way, right? If this is the pivot point, which is positive for us, which means that this one's going to be negative. So there's going to be minus the torque from the question mark, as equal to 0. So plugging in, I'm going to jump straight to this equation. We're plugging in this equation, but I'm plugging in this, is going to be the mass times g times distance on the left. So this is all for the left side. Mass left, distance left, minus mass right times g times distance right is equal to 0. So just to sort of simplify it, I'm going to add this to both sides, making it mass left g distance left is equal to mass right g distance right. Now the reason I've been doing it this way, not plugging in any numbers, is because this formula here, this sort of arrangement, will work for every single level. Okay, so the mass on the left times g times the distance on the left of the pivot point is equal to the mass on the right times g times the distance on the right. And in fact, because we have g on both sides, we can actually cancel it out, and that just leaves us with mass left times distance on the left is equal to mass right times distance on the right. Okay, so I just want to make sure you understand why you can do mass right, distance right, is equal to mass left, distance left, because technically writing this is incorrect in terms of torque, okay? It should be mg, and then you can cancel out the g's to show this, just so when you're showing your work on the test, it is complete. So we're going to do this for every single layer. Of course, technically we will have done all this, but I'm just going to cut to the end, and we're just going to do this for every single layer. So let's start with the first one. So we have the mass on the left is 0.3 kilograms, and the distance on the left is 0.7 meters, and that'll be equal to the mass on the right, which is unknown, so we'll just call that mass right, and distance right is 0.3 meters. You don't have to be a genius to realize that if you divide both sides by 0.3, it's going to cancel this out, and you're going to end up with 0.7 kilograms for that first one. So you got mass right is equal to 0.7 kilograms. Okay, so that's one. So that's this one. So this is 0.7. All right, and this is the next one. So now we're going to do the same equation, mass left, distance left is equal to mass right, distance right. So we have mass left, which we don't know, times the distance on the left, which is 0.25 meters, is equal to the mass on the right times the distance on the right. So now, because this whole piece of the mobile is hanging on the right, then what we're going to do is we're going to add the two masses of each one of these, and that's going to be the same as if there was one mass here equal to these two masses. So this is 0.7.3, which gives us a mass of 1 kilogram hanging on the right. So mass on the right, where is it here? Mass on the right is going to be 1 kilogram times the distance on the right is 0.75. So to solve for mass left, we divide both sides by 0.25. So we got 0.75 divided by 0.25, which is going to be 3. So the mass on the left is going to be 3 kilograms, which makes sense to me. So that's 2, so that's 3 kilograms. And then, of course, for the last one, same deal, mass left, which is now all 3 of these together. So this was 3 kilograms and 1 kilogram. So that's going to be 4 kilograms on the left, times the distance on the left, which is 0.4 meters, is equal to the mass on the right that we don't know, times the distance on the right, which is 0.6 meters. And so we will multiply 4 times 0.4 and divide it by 0.6, which gives us the lovely, let me just make sure I'm doing this right. Yep, the lovely 2.67 kilograms. It couldn't all be nice. So there you go. So divide both sides by, multiply 4 times 0.4, which is going to be 1.6. No. Yeah, 1.6. And then 1.6 divided by 0.6 gives us 2.67. So the mass on the right is 2.67. There we go. That was 1. 2.67 kilograms. Good. All right, let's move on to the next question that I gave you. All right, this one is a little bit trickier. It involves that special technique of moving around the pivot point that we talked about a long time ago. An 80-kilogram window washer is standing 1 meter away from the rightmost cable of his platform. The platform itself has a mass of 100 kilograms. What is the tension in each of the 2 cables? So to start, I'm going to draw a little picture. So here's the left cable, here's the platform. I'm assuming the platform, the cables are sort of all the way at the end. I should have probably mentioned that. And we know that the dude is standing 1 meter away from the rightmost cable. So 1 meter away from here. Window washer. There's a squeegee. And this is 1 meter away. I did not, shoot, I didn't give the actual length of the platform itself. Bummer. Let's say the platform itself is 3 meters. I'm going to update that on the handout, I swear. 3 meters. There we go. So the platform itself we'll say is 3 meters. I apologize for that. I didn't realize I didn't mention that. So this is our diagram. Okay, so our free body diagram, or sorry, our extended body diagram will be the platform, right? And we have to list the forces exerted on the platform. So we've got, we'll call this force cable right. Sorry, I guess that's not the right, that's the left, isn't it? Force cable left, there we go, is up this way. Then we've got force cable right over here. We've got the 80-kilogram man who is exerting the force here, so force man on platform. This is all on platform. And then in the middle, right, so at the center of mass, you have the Earth exerting a force on the platform itself. Force Earth on platform. So there we go. Now, we want to know what the tension is, or what the forces of the cables are on each side. If we put our axis of rotation anywhere other than at one of these sides, then we will not be able to solve for the tension in the 2 cables, or in one of the 2 cables, because we'll have too many unknown values, right? So we won't have this force and we won't have this force. And when we're calculating the torques, we'll have too many unknowns. So the trick here is to set the axis of rotation at one of these two sides to use, the torques to find the force of the one that you didn't use, and then do it again using the other side as your pivot point. So I'm going to start off with the left side as being our pivot point. So we'll call this the pivot point. And that way, so now I'll do this in red, I guess, to show that we're talking about the red pivot point here. So we're looking at the net torque being equal to 0. And I'm going to set counterclockwise as positive again, because that way this is positive, I guess. So if the net torque is equal to 0, then we've got the torque from the cable on the right as being positive, as I said, and then these other two are going to be negative. So minus torque from the earth, and then minus torque from the man is all equal to 0. So plugging in our equations for torque, we have force cable right times the distance on the right, distance to cable right, minus force earth times distance to the center of mass, minus force man times the distance to the man. Now all these distances, as you'll recall from the equation for torque, all these distances are the distances from the pivot point to the force. So this one, if it's exerted at the center of mass, it's going to be halfway. So this is going to be, if it's a 3-meter platform, this is going to be 1.5 meters. Then the man is standing 1 meter from the rightmost side, so this is going to be 2 meters, and then obviously to the other end is 3 meters. And then the other thing we need to talk about is the force. So obviously the force that Earth exerts on the platform is going to be the mass of the platform times g. The force that the man exerts on the platform is also going to be the mass of the man times g. The man pushes down on the platform as hard as the Earth pulls down on the man, if that makes sense. If it doesn't, rewind, play it back slow motion, and listen to it again. So we have rewriting force cable right times, we'll sort of plug in values now, I guess. Oh, no, not yet. Distance cable right minus mass of the platform times g times the distance to the center of mass. Sorry about that. Minus the mass of the man times g times the distance to the man is equal to 0. Now we can plug in our values. So force cable right, we don't know, times the distance from the cable to the right, which is 3 meters, minus the mass of the platform, which I said was 100 kilograms. So 100 kilograms. Notice here I can't cancel g because this expression does not have g in it. I'm going to use g as 10 meters per second squared because it makes things easier. The distance to the center of mass is 1.5 meters. And then minus, once again, the mass of the man, which was 80 kilograms, times g, 10 meters per second squared, times the distance to the man, which we said was 2 meters. So that leaves us with force cable right times 3 minus 100 times 10 is 1,000 times 1.5 is going to be 1,500. Yes. So this is 1,500 minus, this is going to be 1,500, I guess, Newton meters. Minus 80 times 10 is going to be 800 times 2 is going to be 1,600 Newton meters. Is equal to 0. So I'm going to take all of our values and add them together and move them over to the other side. So we have force cable right is equal times 3 meters is equal to 1,500 plus 1,600 is going to be 3,100 Newton meters. And it's added over to the right, so it's positive, and then we divide 3,100 by 3, which gives us 1033 newtons. 1033.3, but let's call it 1033 newtons. There we go. So that is for the right-hand ones. This is 1033. Alright, so now that we're done with that, we can move on to the left cable. And this time, because we know what the right cable is, we can really just put our pivot point anywhere we want, because we know what all the other forces are. But I'm going to go ahead and repeat the same thing, only this time putting the pivot point here. Alright, that changes our distances slightly too. I apologize if this starts getting a little cluttered. So we know this is 1 meter. This is still 1.5 meters, because it's to the middle, right? And then the distance all the way to the other side is still 3 meters, right? So just to put in our values there. So let's do the green one. So, net torque is still equal to 0. But now the torques we have are the torque of the left cable. So torque cable left. This time I'm going to make clockwise positive, because it makes things easier. Again, so this minus the torque from the Earth minus the torque from the dude equal to 0. So we're doing the same sort of process we did before. We have, I'm going to skip this step, right? So it's force times distance, right? So we have the force of the cable on the left times the distance to the cable on the left, minus the mass of the platform times g times the distance to the center of mass from the now right side, right? Minus the mass of the person, or the painter, times g times the distance to the person. Oh, I used man on this side, sorry. Man. Just because it's a window washer doesn't mean it's a man. It could be a woman too. Alright, so there we go. That's going to be our equation. We're going to start plugging things in. So we've got force cable left times the distance on the left, which was 3 meters, to the left cable, which is 3 meters again, minus the mass of the platform, which is 100 kilograms, times g, which is 10, times the distance, which was 1.5 meters, minus the mass of the person, which is 80 kilograms, I'm going to run out of space here, times g, which is 10, times, sorry, I'm going to have to put it down here, times the distance to the person, which is 1 meter. Alright, so just solving it out, this is all equal to 0, don't forget. So solving it out, we have force cable left times 3 meters is equal to, this is going to be the same thing, it's going to be 1,500 Newton meters, minus 80 times 10 times 1, so this is just going to be minus 800 Newton meters. That is all equal to 0. So adding these two things together and moving them over to the other side, our force cable left is equal to, that's going to be 2,300. Oops, I forgot my times 3 meters here. So we divide both sides by 3, and we get 76.66. Not necessarily pretty, but hey, 766. We'll call it. Or we can just call it 767. Either way, I don't care. But there you go. There are your two tensions on either side. Call it 767 newtons and 1033 newtons. All right, there you go. That is everything for torque, I believe. And next time we will pick up with simple harmonic motion. See you then. Bye.